I know.
Resume recording. So today we're going to talk about our last topic. One second. We're going to talk about our last topic today for this. It's not showing my screen anymore. Why does Zoom have to be so stupid? I will never know. We're going to talk about our last topic today, and it's all about empirical. Yes.
Do you have a pencil?
Yes. Haha. I don't know where it came from. It's not mine, but it's there. Feel free to keep it, because mainly I don't know where it came from. So today we're going to talk about empirical formulas. But first, how are we feeling today? I'm a solid 6. What about you guys? 1, 4, maybe a 3. We had a 1. Okay, nice. Everyone that's in person, because you guys can't, the virtual, they look like they're at a 3. Like they might start crying any moment. Probably because, they know chemistry is eventually going to end today, and that makes them sad. So they want to cry because it's going to end. But don't worry, we still have 90 minutes in this class to have lots of fun. 3/5. Okay, I understand. Before we begin, I want to do a little bit of review. So just go ahead and try these 2 problems from yesterday. Can you determine what the percent composition of sodium is in sodium chloride? And what is the percent composition of CnCH4? Here's my calculator. For the people who are online, go ahead and drop your answer in the chat. For the people in person, you can just jot it down on a piece of paper somewhere. And I know you have plenty of paper because I passed it out to you earlier today. Just love percent composition. This problem on your test is worth 5 or 6 points out of 40. So that's a lot of points, That's over 10% of your test grade comes from percent composition. Pretty cool, pretty groovy, if you ask me. I heard that's what the cool kids say now. They say groovy. Oh. So last night, I'll tell you this while you're working on the problem. I was with my parents and we decided to watch a Christmas movie. And we turned on this one. It was a British Christmas movie. We watched about 45 minutes of it, and I could not even tell you what the people's names were or what the plot of the movie was. It was horrible. So then we moved to this other movie with Rob Lowe in it about elephants. And once again, it was called A Holiday Abroad or A Holiday in Africa or something like that. I got about an hour into it, and they never once mentioned anything about it being the holiday season. It was ridiculous. I had no idea what was going on. It was horrible. Because my sister was there, and she doesn't like normal Christmas movies. I was like, let's watch Scrooged. Scrooged is a funny movie. No, they don't want to watch that. Let's watch Four Christmases. No, they don't want to watch that either. Let's watch Christmas Vacation. Yeah. They don't want to watch that either. I don't know if I would agree with that.
What?
It's a Wonderful Life.
That's false.
I love that movie.
Man, come on.
No.
I was gonna say,
Like-
let me guess, you're an elf. You like elf, which I was about to be really.
No, Elf honestly like annoys me.
I like elf, but like it gets way too.
Like I can watch it like once or twice a year, but my youngest sister used to watch it, and she probably still does. She's at Mizzou now. She used to watch it every single day, starting from like Thanksgiving until Christmas.
You don't get annoyed of it.
I don't know, but she would watch it every day, and she would quote it too.
It's so over.
But she would only quote the like, "I'm Buddy the Elf," and I'm like, that's not even a good quote to say. It doesn't make sense because one, you're not an elf, and two, your name is not Buddy. Like it makes literally no sense about like, oh. What do we get for the first one?
39%.
39%. I like the sound of that. Does anyone disagree? Does anyone agree? Yes, we agree. Lily, I hope that's a calculator app on that phone right now. What did we get for the second one? 75, 74.4-ish, between 74 and 76. Sound good? Anyone disagree? Anyone dissent? Even though this isn't a court, so you can't dissent. But you know what? We do what we can. Means like you disagree with the decision. Like if you write a dissenting of like if like the court like the Supreme usually you only get it in like a Supreme Court when there's more than one judge on a case, and if you have like a dissenting opinion, it usually means you voted against whatever the was. So they might write something about how they disagree, and then they like publish it online, and it's kind of petty almost. Like I mean they're important, but like at the same time it's kind of like when like let's say like you disagree with someone's Facebook post, so you leave like a passive aggressive comment on it, or you make your own passive aggressive Facebook post in response to it. It's like the same concept.
You use Facebook.
Do I? Yes. I like I don't post a lot of things, but like I like to keep up with my aunts. They just got on Facebook, so
Yeah, how are you supposed to keep in touch with your older relatives?
yeah, with old people. Yeah, they don't know how to use Instagram. I don't know how to use Instagram. Oh, I posted something. I have a physics Instagram page now for my physics class. It took me like 20 minutes to figure out how to post something to my story.
It's not very intuitive.
And even then I did it wrong, I think, because it didn't like show up for anyone. It was horrible. And then Instagram, like I'm not following anyone on that account. So like you only see your own post. You don't even see all of your own posts. It like filters out posts of your own that it doesn't think you want to see. And I'm like, they're my own posts. Like it's stupid. It's stupid. Anyway, so today we're talking about empirical formulas. And whenever we talk about empirical formulas, we also have to talk about molecular formulas. And the difference between them is the empirical formula is the formula with the simplest ratio of atoms, whereas the molecular formula is what you actually get in nature. So like in this case, we have an empirical formula of HO. Well, a molecular formula of HO might be H2O. So even though it's a different formula, they still have the same ratio of atoms. Like there's still one H to one O, but they represent different compounds. So for every empirical formula, there could be hundreds of different molecular formulas that fit that same empirical formula. But each molecular formula represents a different compound in and of itself. The same thing here is we have glucose, which is C6H12O6, but its empirical formula is CH2O. It's the smallest ratio of atoms. So this is saying that there's one carbon to two hydrogens to one oxygen. And the same thing here is even though it's C6H12O6, there's still only one carbon to two hydrogen to one oxygen. So the empirical formula is the most reduced form of our molecular formula. So like if I give you a molecular formula that maybe looks like, I don't know, Na4S2O8, and I said, what's the empirical formula? I'd say, well, they're all divisible by 2, so I want to divide them all by 2, and the empirical formula for this would be Na2S04. So there's only one empirical formula, but each empirical formula could represent more than one molecular formula, if that kind of makes sense. Whenever I give you this molecular formula and I ask you to sort of say, well, what's the empirical formula? All you have to do is reduce those subscripts as far down as they'll go. Let's say I gave you something that looked like, Ba2SO4. What would the empirical formula of this compound here be? Would it be different or would it just be the same?
Is it the same?
Yeah, it's going to be the same because in this case, because there's only one sulfur, we can't reduce it. So this is already the lowest ratio or the simplest ratio of atoms in this compound. So this here would be our empirical formula for this case. Anytime there's only one of one element, you already know that you have the empirical formula for that compound. So anytime that there's no subscript on an element or the subscript is a 1, you can already say this formula is already in its empirical formula state. Sound good? Are we good with this part of it? So this is one part. This is the simple part of empirical formulas. This is the part you're going to like. You're probably not going to like the next part. I'm just going to warn you about that now. You probably, I like it. You might not like it. So basically the steps to finding the molecular formula from the empirical, or finding the empirical from the molecular, I thought that is you just want to simplify those coefficients down to as small as they'll go to find that simplest ratio of atoms. So like once again, if we had that C6H12O6, because each of these little subscripts here are divisible by 2, we want to reduce that down as far as they'll go. And we could go ahead and say, well, it's going to be CH2. And that's going to be our empirical formula. So the empirical formula is the simplest ratio of atoms, whereas the molecular formula is what you actually have in nature. Now, sometimes we're not going to be given the molecular formula. Instead, we're going to be given data, and we have to find out what the empirical formula is. And there's really 2 main steps to this. So the first step is we want to calculate the number of moles. So like we're going to be given that maybe a sample has 35 grams of barium and 10 grams of fluorine. And we're going to say, well, what is the empirical formula? Well, our first step is we have to convert any grams that we're given into moles of each atom. So that's step 1. And then step 2 is we want to take the smallest mole number and divide all of the other moles by that. So like whenever we calculate the number of moles, we want to take that smallest number and divide all of the other numbers that we calculated by the smallest mole number, and that is going to give us our empirical formula. And I'm going to walk you through an example because it sounds confusing whenever it's up here just in the words, but I promise you it is not as confusing as it looks. Do I need to stand off to the side or am I good here? Okay. So, what does this look like when we actually have a problem? So in a typical empirical formula problem, we know it's going to look something similar to this. So a compound is known to contain 28.4 grams of copper and 71.6 grams of bromine. What is the empirical formula? Well, our first step is we need to convert what we have into moles. So we have this 28.4 grams of copper and we have 71.6 grams of bromine. So how do I go from grams or mass into moles?
On our paper, we have like 28.4%, not.
Change the percent to grams.
Okay.
Yeah, sorry, I forgot to do that. I was going to simplify this example because you don't ever see the percentage in this class. Yeah, so change the percent to grams. So we have 28.4 grams of copper and 71.6 grams of bromine. So how do we go from grams to moles? Not multiply. You want to divide. Anytime we go from grams to moles, we divide by the molar mass. So we're going to find our grams of copper, we're going to take that 28.4, divide by the molar mass of copper. Oh, which is, 63.5 divided by 63.5. And whenever we do that, we find that we're going to have 0.447 moles of copper. And then we want to find the moles of bromine. So we're going to take that 71.6 grams of bromine divided by the molar mass of bromine, which is, I wish these numbers were 79.5. Divided by 79.5. So 71.6 divided by 7.5, and we find that we have 0.901 moles of bromine. So that's step one, it's just converting it into moles. So we just take however many grams of each substance we have and divide it by the molar mass, and that's going to give us how many moles. And that's all we have to do for step one. So we're done. We can then move on to step two. So we want to divide by the smallest mole number. Sorry, this is just slightly off. I'll rewrite that as 0.900. We want to divide by the smallest mole number. And all that means is we look at the number of moles that we have, and whichever one is the smallest, which in this case is copper, we're going to divide all of our other moles by copper. So we're going to divide everything by 0.477 or 0.447. So divide by 0.447. And divide by 0.447. 0.447 divided by 0.447 just gives us 1. And whenever we take 0.900 divided by 0.447, we get that's going to be equal to 2.0. For these, you're always going to want to round to right around 1 decimal. As long as our numbers are close to a whole number, so it's close to 1 or 2, it's not like 2.5. As long as it's less than 2.1, we can just go ahead and round down to the lowest number. Or if it's like 1.9, we could round up to 2. Our last step is we write out the symbol for each element. So we have Cu and Br. And the number that we calculated here after we divide by the smallest mole number becomes the subscript on our compound. So the empirical formula for this compound here would just be CuBr2. And remember, anytime in chemistry that we see a 1 on our little, compounds here, we can just say we're not going to write it because we don't care about 1s, because 1s are stupid. No one likes a 1. No one's happy if you get 1 Swiss roll. No, Swiss rolls come in packages of 2. So where did the other 1 go? It went to somebody else who probably doesn't deserve it. Although you guys will be happy with 1 package of Smarties today, because each package of Smarties contains more than 1 Smartie.
But it is a Smartie.
So, would you rather get a Dum Dum?
I mean,
Yeah, actually.
Oh, okay. I have Dum Dums too.
I'd rather get Skittles.
Yeah.
I mean, I have Skittles too.
Give us Skittles.
I could. Any questions on this problem though?
So whenever we do we actually write out the formula all the way around.
Yeah, this next example I believe is going to be one where you don't. So sometimes sometimes when you do this division, you'll get something that'll be 2.5. Anytime you get a 0.5, you want to multiply both of your numbers by 2. Because you can't have, and the reason why is, let's say this was 2.5 and you had CuBr 2.5, you can't have half a bromine atom. It's physically, if you cut a bromine atom in half, you would have a different element because you would only have half the number of protons. So you wouldn't even, you would have a completely different element. So you can't have half an atom, or you can't have a third of an atom. So as long as it's close to a whole number to begin with, you can just round. But if it's 2.5, you got to multiply everything by 2. If the next one's not an example, one of the ones on the worksheet is an example like that, and we can go through and do that one together to show you what I mean by what happens if it's 2.5. In this example, we have a compound that contains 26.45 grams of aluminum and 20.85 grams of oxygen. What is the empirical formula? Step one, I have to convert everything into moles. So if I look at aluminum, I'm going to take that 26.45 grams of aluminum, 0.45, divided by the molar mass of aluminum, which is something. 26.98. Divided by 26.98. And when I do that and I put it into my fancy dancy calculator, unless you want to like do it out by hand, I mean, that's perfectly fine. I don't care. I mean, I wouldn't, but you get right around 0.98 moles. And then we're going to take our 20.85 grams of oxygen and divide by the molar mass of oxygen, which is 16. So 20.85 divided by 16. And we're going to get 1.3. Our next step is we're going to divide by the smallest mole number. So divided by 0.98, divided by 0.98. We get a 1 here. And we get 1.3 here. So this is one example where we couldn't just round this number because it's a 1.3. Anything below like 1.1 you can round, or anything above a 1.9 you can round, but a 1.3 we cannot round that. So what do? Well, we have to multiply by numbers, and we have to multiply by a whole number until we get whole numbers here. So if I kind of look at this, or just, I guess, you know, usually I say trial and error, but I'm just going to tell you now because I don't like trial and error. If you see a 0.3, you're going to want to multiply everything by 3. And if you see a 0.5, you're going to want to multiply everything by 2. You will not get an example problem that is anything other than these two by a 0.3 or a 0.5. And if you do, I'll help you out with it. So in this case, it's a 0.3. We're going to want to multiply everything by 3. So this would become a 3, and this is going to become a 1.9. And 1.9 is close enough to, or not 1.9. 3.9. 3.9 is close enough to 4 that we can just go ahead and say we're going to round that up to 4. We write out our element symbols. The 3 goes to the aluminum, and the 4 goes to the oxygen. So then this would become Al3O4 would be our empirical formula for this problem. Yeah, so anytime you have a 0.3, you're going to want to multiply by 3, and anytime you have a 0.5, you're going to want to multiply by 2. Any questions on empirical formulas? Okay. Just to sort of sum everything up, the empirical formula is just the simplest or the reduced ratio, not ration, of the atoms in a formula, and the molecular formula is the actual formula for the compound that we're talking about. So the empirical formula is the simplest version, whereas the molecular formula is what you actually have in nature or in an experiment. Today, because I know we have tons of extra time, because it is only 10:29. You have a full hour today. I've been noticing that there is a ton of missing work. I'm not going to specify who is missing work, but there is a ton of missing work so far for this unit. So for the rest of the day, I want you to work on anything that you're missing. So far for this unit, we've had that first mole conversion little Canvas assignment, well, for one-step conversions. We have the two-step mole conversion assignment on Canvas. We have the percent composition assignment from yesterday, which is a Google Cloud document. And then we have the empirical formula assignment from today, which is also a Google Cloud document. So there are those 4 assignments from today. I want you to try and get those all finished up today if possible, or by the end of the night. That way tomorrow when we review and do our little lab activity, you can ask questions if you have them, or if you don't understand something, we can clarify that. So I'm going to give you the rest of the time to work on those assignments. I would love for you to stay on the Zoom. However, I'm not going to require it because I know sometimes working on Zoom can be hard, especially when you have to have Canvas open and all this other stuff. But I do want those assignments done today by midnight. I'll be sending you lots of emails if they're not done. I don't like sending emails, so they might get more and more passive aggressive as the day goes on. Who really knows? But like I said, you're more than welcome to log off, or if you want to hang on and stay on, you can do that as well. I'll be here to answer any questions.